Okay, so now we're going to be discussing about logic gates. Now, previously, we got an introduction to what digital logic is all about. But in order to represent logic, the logical part of it, we have to use what's called logic gates. Now, just in general, there are many logic gates that we care about. The three basic ones is a NOT gate. So, NOT gate. So, the symbol for this looks like this. The actual part of what makes this a NOT gate is this symbol right here, this circle, which is to say this is inverse logic. So whenever you have A, you'll pass it through a NOT gate, and this becomes what's called a complement, which we use a bar. Sometimes we say A to C, sometimes we say A prime. They mean the same thing, but to keep it consistent, we'll use this instead. Now, the next one is called an AND gate. So an AND gate means that both statements have to be true in order for the statement to pass. In a way, you can think of it as multiplication. So if you have two statements, A and B, and they pass through an AND gate, which is represented by this symbol. Now, just to kind of help the viewer, usually I would put AND gate explicitly because AND and OR gates are very similar to each other. So it's good to kind of always kind of spell it out. So AND gate looks like this: A times B. Later on, later on in this video, we'll talk about their truth table. But for now, this is just the three basic gates that we care about. So we have then an OR gate. An OR gate means that only one statement has to be true in order to pass. So in essence, that either statement can be true and the whole statement will be true. In a way, this is like addition. If this wasn't true, then if this was true, this will pass. So this looks like A plus B. And those are just the three gates that we see. Now, note that these are ideal models of logic gates. We'll discuss later on what I mean by that. But for now, just take it for granted. These are the three basic gates that we care about. Now, here's the truth table for a NOT gate. A truth table means that we test each binary value, and based on the property of the gate, will give us as specific output. So here's the output for a NOT gate. We have an input A, and we write it like this. And here's our output, which we would put as an O or a Q. We'll use Q. We have a 0 and a 1. So every time that A is 0, Q is 1. And every time that A is 1, Q is 0. Kind of the opposite. Now, what about an AND gate? Well, to kind of briefly describe it, something and something have to be true in order for this to be true. So we have four statements: 0, 0, 0, 1, 1, 0, 1, 1. Now, just to kind of briefly show it, if neither are true, this is not true. If only one is true, not true. If only the other is true, not true. Both have to be true in order for this output to be true. Lastly, we have an OR gate. OR gates are more easier to understand in the sense that OR gates are a little more forgiving. So we have Q as given below. Anytime one of them is true, then the output is true. If neither are true, then there's no output. But if one of them is true or both of them are true, then the output is true. And that's just the truth table for NOT, and OR gates. Now, there are more gates, and I will talk about them instead in the next video. But for now, as a brief introduction, these are what logic gates are. They're a way to represent the computer logic when we are saying something like, do you want this and that? Do you want this or that? Do you not want this? So we'll talk about the special kind of gates in the next video. Okay, thank you.